Hello, my name is Ron Mitchell, and my project is a case study in medical diagnostics. I am currently working with malaria detection based upon blood cell images. Malaria is a life-threatening disease caused by mosquito bites from mosquito-carrying Plasmodium parasites. In 2017, there were 219 million malaria cases in 87 countries. Based upon research from the World Health Organization, African regions were home to 92% of malaria cases and 93% of the malaria deaths. This disease is preventable and curable, however, diagnosis is tricky. The first symptoms of malaria do not appear until 10 to 15 days after being bitten by an infected mosquito. The symptoms are very similar to the common cold, such as fever, chills, headache, etc. Given the fact that malaria is an infrequent disease in countries like the United States, healthcare professionals are less likely to be familiar with this disease and may not order required diagnostics tests for malaria. Conversely, in regions like Africa, where malaria is frequent, residents often recognize the symptoms and treat themselves with ineffective home remedies without seeking diagnostic confirmation, as medical care is normally short-handed and unaffordable. If left undiagnosed and untreated or incorrectly treated, malaria can progress to severe disease and lead to death. I believe that deep learning could help improve the malaria diagnosis process and accuracy and thus reduce the cost of diagnosis. The goal of my project is to create a convolutional neural network model for binary classification to predict whether or not a given blood cell image is infected with malaria parasites. Core technologies used for the project are Python and Keras for CNN development, Google Colaboratory for a GPU platform, and Python packages such as NumPy, Pil, Matplotlib, Pandas, scikit-learn, etc. My inspiration behind the project is to use deep learning methodology towards saving human lives by detecting malaria with high accuracy. The dataset for the project comes from the U.S. National Library of Medicine. It is also available publicly on Kaggle. Here is the website for Kaggle dataset link. The data contains over 27,000 images of blood cells with equal count of infected and uninfected cells. The total size of the dataset is 337 MB and comes in a zip file. For installation and configuration, let's jump to the demo. Here is the Kaggle dataset. I created my Google Colaboratory notebook and set it up to use the GPU. Then I set up a download to the Kaggle dataset directly using the Kaggle API so that I don't have to upload it from my local laptop. That saved me time and resources. You can download a dataset zip file from Kaggle on your local machine and then upload it to your Google Drive if you like. If you are interested in downloading it via API like I did, here is a recipe for it. First, I created an account on Kaggle and downloaded the Kaggle.json file. And uploaded that Kaggle.json to Google Colabs. Then I installed Kaggle API via pip install Kaggle. This installs Kaggle API client. Couple steps to move Kaggle.json to a local location expected by Kaggle, which is at the root, and setting up permissions to avoid warning a Kaggle tool startup. That's it. At this point, we are ready to download any data available on Kaggle. To download the malaria cell image dataset, we need its API key from Kaggle. Let's go to Kaggle. I got the API key and then I pasted it in the command. Kaggle dataset download. This starts downloading the zip file from Kaggle containing cell images. Then I unzip the zip file and it creates parent folder names cell images. Within the folder, it has two subfolders named parasitized and uninfected. Each of the subfolder holds a blood cell images in PNG format. Both subfolders have equal number of cell images. After getting all the data, I'm ready to do the experiment. For setup and pre-processing, I created a folder structure for train, validation, and test for each of the two classes. I decided to use 50% images for training, 25% for validation, and 25% for testing. I rescaled the images to 1/255 and resized them to 154 by 154. Let's go back to the demo. Here I am creating folder structure to train, validate, and test sets for both classes. Then looping through all images to place 50% of the images in the train folder, 25% in the validation folder, and 25% in the test folder. Checking to make sure I've received expected counts of images to train, validate, and test the infected and uninfected classes. Here is a sample of the infected and uninfected blood cell image. Here is a pre-processing routine where I rescale the images to 1/255 and resize them to 154 by 154. At this point, we're ready to create the first model. My action plan for implementation was: first, create my sequential CNN model using Keras. Perform hyperparameter tuning to get optimal learning rate in epochs. The model trained well for 40 epochs, however, ran into overfitting at epoch 10. Second, I created model 2 using L2 regularization in an attempt to improve the overfitting issue. Third, I created model 3 using image augmentation in an attempt to improve overfitting issue. Fourth, I created model 4 using L2 regularization from model 2 and image augmentation from model 3. I applied the accuracy of all 4 models on unseen images from the test dataset to pick the model that gives the highest accuracy. Then I used the CNN model to predict classes for 3 unseen blood cell images, which it predicted correctly. Finally, I calculated precision, recall, and F1 score for each class using predictions from my CNN model, and I plotted a confusion matrix for the predictions on unseen images from test sample. Let's go back to the demo. This is my first CNN model with alternating convolutional layer and max pooling layer 4 times, followed by a flattening layer. This is my binary classification problem, and I am using a sigmoid activation function. This model, which ran for 40 epochs with a learning rate of 1e-4, I gave accuracy of around 95% of the validation set, however ran into overfitting at epoch number 10. So I created model number 2 with L2 regularization with lambda equal to 0.0005. Let's take a look. This model ran for 40 epochs and gave accuracy of little over 95% and ran into overfitting at epoch number 15. Next, in model number 3, I used image augmentation techniques. Let's look at the code. Working with blood cell images, the vertical flip and horizontal flip image augmentation operations made most sense for this use case. I used Keras image data generator to augment training images. Here's a sample of one blood cell image after a few vertical and horizontal flip augmentation operations. I used augmented images to train my model 3. This model ran for 40 epochs and gave accuracy over 95%, and overfitting shifted to epoch 20. Finally, I decided to use L2 regularization and image augmentation techniques together in model 4. I used L2 regularization with lambda equal to 0.00005, and I used Kira's image generator for vertical and horizontal flip augmentation operations for training set. Validation was not augmented. Model 4 trained for 40 epochs and gave the highest validity accuracy of 95.61%. Now we are ready to pick the best models so far. At this point, I provided unseen images from the test set to all 4 models and plotted the accuracy of the models. Model 4 showed the highest accuracy of close to 96% on unseen test blood cell images. So I decided to choose model 4 as my final CNN model for the experiment. At this point, I provided 3 unseen blood cell images to my CNN model to review the predictions from the model. The first 2 blood cell images, ending in 36 and 233, were uninfected, which model predicted accurately. The last image, ending in 96, was infected, which model predicted accurately. Next, I was curious to understand the performance of the model for each class. So I chose to calculate precision recall and F1 score for each class for predictions by CNN model. I used scikit-learn's classification report for this purpose. Finally, I plotted a confusion matrix for the CNN model predictions on test set images. Let's look at the code. I used scikit-learn's confusion matrix function to do so. The CNN model predicted 95% of infected images correctly, and it predicted 93% of uninfected images correctly. This completes the demo. In summary, I believe using L2 regularization and image augmentation were very helpful techniques for the CNN model. Use of vertical flip and horizontal flip augmentation operations were most appropriate in this case amongst all available augmentation operations. Malaria parasites can be identified by examining under the microscope of a drop of a patient's blood, spread out as a blood smear on a microscope slide. Prior to examination, the specimen is stained to give a parasite a distinctive appearance. This technique remains the gold standard for laboratory confirmation of malaria. However, it depends on the quality of the reagents, quality of the microscope, and the experience of the laboratory staff. With this being said, I think certain images from the training data set can be improved upon by taking them from a higher quality source, which will help the model accuracy, in my opinion. Next steps, I would like to compare performance of this model with some of the pre-trained CNNs like AlexNet, VGG16, etc., for feature extraction these type of blood cells. I also think that a higher percentage of images as training sets, typically an 80-20 split, will be helpful to increase the accuracy of the model as well. Here are the references for the project. I hope you find this video useful. Thank you for watching.